Hello everyone, it's me, Mr. Younger, Billy Younger. I am here to teach you how to use the volume expansion formula in a very specific case. So I'm going to switch over to my iPad by sharing that with you, and then we'll read the problem and get started. All right, so now we have the problem visible on your screen on my iPad screen as well. It says an 80.4-liter gas tank is made of steel and filled to the top at 15.7 degrees Celsius. The car was immediately parked in direct sunlight, and eventually the tank and gas reached equilibrium at 40.0 degrees Celsius. How much gas will overflow the gas tank once the new temperature was reached? Or I should say is reached, but either way, you get the point. So what we have to use here, of course, is our volume expansion formula. And our volume expansion formula I can give you as follows. Just like before, there's a version for the change in. So there's a version for the change in volume in this case. And we expect that would be proportional to the initial volume. So I'd put V0 there. The constant proportionality in 3 dimensions, which is what a volume is essentially the same as 3 times alpha in almost all cases. But that 3 times alpha is also called beta. So I'll put beta there and then times delta t. Of course, the other version would be V final minus V0 is equal to V0 times beta times delta t, which you can make V equal to V0 times 1 plus beta times delta t. But that's not the version we're planning on using. We're going to use this first version, the delta V one. The other things we'll need to know, of course, is when the car starts to heat up, the gas in the car is going to get hotter, as well as the gas tank itself get hotter. And by this problem's example, it's saying that you're going to increase to 40 degrees Celsius, 40.0 specifically. So what we know is the tank, which is a hollowed out hunk of steel, the air inside of the tank is, or I should say, the inside edges of the tank are going to act just like a large chunk of steel that you could imagine, in some sense, scraping out of the tank or transporting out of, like in Star Trek sort of thing, transporting out the actual steel material that would otherwise be exactly where the gas is. So what we've learned is evidently if you pull a chunk of material out of another bigger chunk of material, then the whole acts just like the material that was taken out. So we're treating the material taken out, the air in this case, as if it were steel. So yes, the tank is going to expand because of an increase in temperature, and the gasoline is going to expand because of an increase in temperature. But the expansion of the tank will lessen the amount of overflow that the fuel, or the amount of overflow of the fuel. So we have to do basically a delta V for the tank, or actually I should say a delta V first for the gas, and then subtract from that the delta V for the tank. Now, in order to do that, I do need some figures. So for instance, the beta for iron or steel is actually 900 and, or excuse me, no, that's the gas one. Yeah, that's the gasoline one. It's 35 times 10 to the negative 6 reciprocal Celsius degrees. The beta for the gasoline is actually equal to 950 times 10 to the negative 6 Celsius degrees reciprocal. So our V overflow would be delta V gas minus delta V for the tank, which we'll just call iron. So that should be our answer. Now we can go ahead and calculate each of those. Delta V for the gas is going to be, we have to put in the beta first, and the beta is, for the gas, is 950 times 10 to the negative 6 reciprocal Celsius degrees times the initial volume, which in our case was 80.4 liters, times the change in temperature, which will be 40.0 degrees Celsius minus 15.7 degrees Celsius. Now, this actually leaves 3 sig figs after you do the subtraction, 40 minus 15.7. The zero on the 950 is likely not significant. So we really can only put out 2 sig figs, but I'll keep a couple extra just in case the difference between the two is not actually measurable. So in terms of sig figs. So let's go ahead and do this calculation. I say 950 times 10 to the negative 6 times 8, 0.4 times parenthesis 40.0 minus 15.7, and that gives me a change in volume equal to 1.8560, and that is of course in liters. And since we only had 2 sig figs, that means this has 3 non-sig figs in it. So we'd actually technically need to call this 1.9 if we're doing the traditional 5 or biggers round up. If we were doing something weird like the 5, sometimes when there's a 5 in the digit to the right of the one you're supposed to round to, some people will say, well, you look at the next digit, which in our case is a 6, and if it's even, you round up. If it's odd, you round down or something like that. We're not doing that. We're just going straight out with a 1.9, no matter what the digit after the 5 is. So that's how much the gas will expand by, 1.8560 liters. Now we want to find out how much the actual tank is going to expand, because that will accommodate some of this leakage. And prevent it from being leakage for that matter. So the delta V for the iron, again, we're imagining the inner part of the tank as if it's made of, instead of air, as if it's made of steel, and then we're calculating what that steel would behave like, and that turns out to be exactly what the inside of the tank behaves like. So in this case, we're going to write 35 times 10 to the negative 6 reciprocal Celsius degrees times 80.4 liters, which is, of course, the volume of the tank, and times 40.0 minus 15.7 degrees Celsius in both cases. So I'll put those in parentheses. So now when I do this math, I get 35 times 10 to the negative 6 times 80.4 times parentheses 40 minus 15.7 in parentheses, and this gives me 0.0683. Again, the 35 has only 2 sig figs. The 40 minus 15.7 actually left us with 3, but we're limited by the 2. So really the 3 and the 8 are not sig figs. So we can now say that the total overflow would be 1.8560 liters minus 0.0683 liters. Notice the 6 is in the hundredths place, and when we look at our numbers for the, well, I say the 6 in the second part of the subtraction, the number being subtracted, that 6 and that 8 are the sig figs, and that 6 is in the hundredths place, the 8's in the thousandths place, and so on and so forth. But we see that we only come up to the hundreds place, or excuse me, to the tenths place on the delta V for the gas. So they don't even line up. That's what I was talking about, our concern that we might not, quote unquote, be able to measure the change. But the good news is we do the subtraction. So I'm going to take 1.8560 minus 0.06838. I can subtract those, and ultimately the result would be 1.78, and we'll keep 2 more digits, 76 liters. But again, our only significant figures here extend out to, since we're doing subtraction, it extends out to 1 decimal place. So the 8, the 7, and the 6 here are not sig figs. So we'd say roughly 1.8 liters of fuel would overflow out of the tank. And of course, that's the danger of completely overfilling your tank. If it doesn't have a relief where that can happen, which you would like, then there would actually be a problem in that you call the tank to explode, not necessarily in a fiery explosion, but due to a pressure explosion, and that could lead to fire. So we're going to ultimately just say that this answer is about 1 point. I should say 1.8. I don't know why I started writing in red. We're going to say that's about 1.8 liters is overflow. So hopefully that gives you a little look into how we use the delta V equals beta V0 delta T formula. And that's about it. Have a good day.